Good morning, good afternoon, and good evening to everyone joining us today for another webinar from the Megger webinar series. My name is Tilsan Adnan, and I'll be the moderator for the session today. So today's webinar topic is breaking conventions in circuit breaker testing, which we will present a modern approach. So in this session, you will learn the modern approach used to conduct these tests in the field. Speaker for today's session is Mr. Ali Azzam, who's an application engineer in Megger Middle East for the protection testing segment. So before I hand over the mic to Mr. Ali Azzam, I would like to highlight a few things. You are all muted to avoid any disturbance during the presentation. You may submit any questions at any time during the presentation, and we will answer through in the Q&A session at the end of the presentation. Please note that the slides and the video will be shared within the next 2 days after the webinar. Also, the certificates, you can request them through a link that we will share at the end of the session, and you will receive it within the next 10 business days. So as you see in the screen right now, this is how where the chat is, and you may submit your questions in the chat box at any time. Also, you may use the raise hand feature at the end of the session to verbally ask your question directly to the presenter, and we will answer your question either in Arabic or English. So this is how the survey questions will look like. Through this, you can request either attendance certificate, product demo, or a quotation. So lastly, if you are interested in more Megger webinars, please visit us on www.megger.com/webinars. And I would recommend you to follow us on social media accounts, Facebook and LinkedIn, to get all new updates about products and webinars. If you have further questions, please submit them on memarketing@megger.com. So I hope you enjoy the session. I will now hand over the mic to Mr. Ali. Over to you.
Thank you, Susan, for the introduction. And thank you all for taking your time to attend this informative webinar. So let me just share my screen. Okay, can you see my screen? Okay. Can you see my screen?
Not yet.
How about now?
Yes, now we can almost see it. Yeah.
Okay, just. Okay, I apologize for that. So our topic today will be about circuit breaker testing. So first, we'll have an introduction about different type of circuit breakers. We will differentiate between the low voltage and medium and high voltage circuit breakers. Then we'll dive into the types of medium and high voltage circuit breakers and talk about the different components of the circuit breaker. After that, we'll move on to testing. We'll talk about different testing or different tests like contact resistance test, circuit breaker timing test, travel and motion test, coil current and DRM tests, and why each test is important. After that, we will talk about some of our solutions, and finally, we'll have a Q&A session to answer your questions. So let's start with the difference between low voltage and medium and high voltage circuit breakers. Low voltage circuit breakers are breakers that are usually rated below 1000 volts. They trip on their own when there is too much current, so there is no need for external equipment like relays. Timing test for this relays is usually done by means of primary injection, so you'll inject actual fault current to get the reaction type of these breakers. We have many different types. Some examples include MCBs, miniature circuit breakers, MCCBs or molded case circuit breakers, and airframe circuit breakers. As for medium and high voltage circuit breakers, they are usually rated for higher than 1000 volts, and they cannot trip on their own. They need external signals to trip, like a signal from a relay. Timing test is usually performed using a time and travel analyzer or circuit breaker analyzers. Let's go into details with the different types of medium and high voltage circuit breakers, which will be our focus today. We'll be focusing mostly on medium and high voltage circuit breaker testing. So the first type is live tank circuit breaker. Its interrupter is on a insulating support or structure, and its tank is live, like near to line voltage. This is because it has lower insulation and its body is not grounded. This type of breakers require standalone CTs. On the other hand, we have a dead tank circuit breaker. It has a grounded body, so zero potential between the body and the ground. That's why it requires more insulation. Its CTs are usually mounted on the bushing of these circuit breakers, and this type of circuit breakers has more stability during earthquakes. Another type is GIS, or gas insulated switchgear. This type is usually indoor, and in this type the whole switchgear is insulated inside a chamber by SF6 gas. The tank is insulated and grounded, and it's usually used in space-limited environments with harsh environments like dust and high heat. It can be either installed outdoors or indoors. We also have a type called vacuum circuit breakers, or VCBs. In this type of circuit breaker, the insulating medium is vacuum, so there is no gas or material inside, it's basically vacuum. And it's usually used in medium voltage or distribution networks. It is very compact and relatively low maintenance. And because there is no gas inside and no material, there is no arcing during interruption. The final type we'll discuss today is generator circuit breaker, or GCB. It is used to protect generators and has high continuous current rating. Older designs used air blast technology, and the newer designs uses SF6 gas. Now we'll talk briefly about the components of a circuit breaker. Let me take the pointer. So you will have an incoming conductor and an outgoing conductor. And between them, you will have the interrupter. Okay. Inside the interrupter, you have two contacts. One is a moving contact and one is a fixed contact. And you have the mechanism that moves the moving contact using the linkage system. Finally, we have the control mechanism where we have the trip and close coils for controlling the circuit breaker, as well as the charging motor. Moving onto interrupters, we have many types of interrupters, like VCB interrupters, vacuum circuit breaker interrupters, and SF6 interrupters. For VCB interrupters, they consist of two plates inside a vacuum bottle. As for SF6 gas, what's special about it is that it has two moving contacts and two fixed contacts. So the outer one here is the main contact, and the inner one is the arcing contact. The arcing contact is used to suppress the arc. It's made of special material that can withstand the high heat of the arcs. And it's usually the first one to close and the last one to separate during the open operation. This is a real picture of an SF6 interrupter. You can see the main contacts, the bigger one, and this is the arcing contacts. And this is a cross-sectional view of it. We have the arcing contacts here. Sorry, the main contacts here and the arcing contacts here. And this is the two conductors, outgoing and ingoing conductors. The second component of circuit breaker is the operating mechanism. It generates and stores the energy and releases it to perform a close and open operation in milliseconds. This mechanism also moves the auxiliary contacts. These contacts are used for two things. One, to show us the status of the breaker, and to protect the closing and tripping coils. We also have a position indicator, shows the status of the breaker, and an operation counter. Each time the breaker operates, this counter will increase. We also have a charging indicator and a dashpot to prevent mechanical damage for the breaker, to absorb all that kinetic energy during the opening operation. There are different types of mechanisms. We have a spring type, magnetic type, hydraulic type, and pneumatic type of mechanisms. We can also classify them onto two types: gang-operated and independent pole-operated breakers. For gang-operated breakers, they are usually for voltages below 245 kV. And in this type, all three phases are operated with one mechanism. For independent pole operated breakers, they have three mechanisms for each phase, and they are usually for breakers higher than 245 kV. They can also trip and reclose single phase only for single phase faults. So here are some examples. We have a common mechanism. We have one mechanism for controlling all three phases. And here we have a separate mechanism. We have one mechanism for each phase. And each mechanism will have its own control circuitry with its own tripping coils and closing coils. This is another example. We have one mechanism here for all three phases. And here we have one mechanism for each phase. The third component of the circuit breaker is the control circuitry. This is a simplified diagram of the control circuit of the closed coil and the trip coil. We have the closed coil here, and we have above it the 52A contacts. These contacts, the 52A and 52B contacts, move with the breaker. So we can see the status of these contacts here. The 52A is always in sync with the CB status. So when the CB is open, the 52A is open and the 52B is closed. When the circuit breaker is closed, the 52A is closed and the 52B is open. So we also have here a series of contactors that open and close to allow us to energize or to energize the closing coil and tripping coil. So the mechanism is not ready. These contactors will open and we will not be able to energize these coils. So basically, when we are testing, we will connect the testing leads for controlling the tripping and the closing coils on the positive and negative side of these coils. Now we'll talk a bit about the important properties of a circuit breaker. The circuit breaker has three main jobs. It has to be a good conductor when it's closed, and it has to be a good isolator when it's open. And it has to, when opening, it has to be opened quickly to extinguish the arc. So for the first point, to verify that our circuit breaker is a good conductor, we usually perform static resistance measurement. And to verify that the breaker is operating correctly during the open or close operation, we do timing test, travel test or motion test, and dynamic resistance measurement, as well as coil current analysis. Finally, for verifying the isolation of the circuit breaker or the interrupter, when it's open, we do insulation resistance test, as well as power factor or tan delta test, partial discharge test, as well as vacuum integrity check for VCBs. The first test we will talk about is the static resistance measurement. This test is important because when we have high resistance in the circuit breaker contact, this can lead to power losses. When you do the test, you verify that the contact should be typically around 20 to 50 microohms. Generator breakers are a special case. They are usually less than 1 microohms. So how we test these breakers is the following. We have to close the breaker, should be in the closed state, and we inject DC current and measure the voltage drop across this contact. After that, we can apply Ohm's law. The IEC standard specifies that you have to use a minimum of 50 amperes for testing static resistance, and the IEEE states a minimum of 100 amps. We use 4-wire method for this test to remove the effect of the test leads. We use only 2 wires. They will be included in our measurement. We can also perform this test while both sides are grounded, and we can use a clamp to remove the current that's going through the earth loop. So why the 50 amps requirement in IEC and the 100 amps requirement in the IEEE standard? There are many reasons. One reason is to eliminate the effect of noise and limit the influence of thermal EMF. Also, we might have some contamination on our contacts. When you use higher currents, this contamination might get burned, and we will get a proper reading. About this thermal EMF, there is another method for eliminating it. You can perform the test one time, then reverse the polarity and repeat it again and take the average measurement. This will eliminate the effect of thermal EMF on your reading. The second test we will talk about is the timing test. In this test, we measure the opening and closing time of the circuit breaker interrupter. This is done by connecting the leads to both sides of the breaker to continuously monitor its status during the opening and closing while testing. Timing tests are made to determine the time required for circuit breakers to operate on open, close, and close open, as well as reclose operations. It is done during the production of the circuit breaker to check the operation of a new CB is within the speed range selected during the development of this specific type of circuit breaker. And It is done also during service as a part of routine maintenance to determine whether it is still operating correctly. This is done usually by the use of a circuit breaker analyzer. First, the timing leads are connected to both sides of the breaker to continuously monitoring it. And another set of leads is connected to the closed coil and operating coil to control the breaker. So once we give a open command, for example, for opening time test, the built-in timer in this kit starts, and when the status of the circuit breaker changes, this time will stop, giving us the result. There are many test sequences for the timing test used to simulate different conditions. The first is the close test, measured by the time difference from energizing the closed coil till the contacts close. And it is important to do this test at rated control voltage of the coil, because if you reduce this voltage, it might take a longer time to close and open the breaker. The second one is open operation or opening sequence. It is measured by the time difference from energizing the trip coil and the instant when the contacts separate. Another one is the close open sequence, or it's called trip free. It simulates closing onto a fault or switch onto fault condition. This is used to demonstrate that the breaker is free to trip even when the close signal is still on. Next, we have open close sequence, which is used to simulate a recloser operation of a circuit breaker. The pulse timing for this sequence should be according to the specs of the specific breaker or specific manufacturer. The final sequence is open close open sequence, and it's used to simulate a recloser operation where the fault is still there. So unsuccessful auto reclosing, let's say. These are the important parameters we get from the timing test. First, we have the close and opening time. We compare the closing and opening times to the reference values and tolerances that are usually available with the circuit breaker manual from the manufacturer. As for comparing different phases together, the time difference should be less than 1/4 of a cycle for the closing operation according to the IEC standard, and 1/6 of a cycle during the opening operation. When comparing time for interrupters in the same phase, so if you have a circuit breaker, especially when dealing with extremely high voltage, you have multiple interrupters per phase. So when comparing these interrupters within the same phase, the time limit will be 1/8 of a cycle during the opening operation. You can also get information about the timing difference between the 52A and 52B contacts compared to the main contacts of the circuit breaker. However, there is some hazards when performing this timing test, especially using the conventional method. When a circuit breaker is taken offline for testing, both sides are grounded. If you want to take or to perform a timing test with the method we just discussed, you will have to remove one side of the circuit breaker. This is because the ground loop has a very low resistance, and it will be in parallel with the main contact that you are trying to perform a timing test on. So you will always get the breaker status as closed. So to fix that, they remove one side of the grounding to perform the test. This raises a security or safety issue because you might get electrocuted. And secondly, this induced voltages from nearby conductors or from the adjacent bay, if it's not de-energized, can affect your reading, give you wrong results, or in some cases, if the induced voltage is too high, it can damage your equipment. And when you are removing the ground, you might get some arcing, which can cause burns to the operator. To combat these safety concerns, Megger introduced a technology called dual ground timing by the use of a dynamic capacitance measurement. The way this works is that instead of using continuity measurement, our instrument looks at the circuit breaker as a variable capacitor. The two parallel plates are the fixed contact and the moving contact. When the circuit breaker operates, the moving contact moves, so the distance between these two plates changes the capacitance values. This variable capacitance, together with the cable inductance, which is the HV conductor and the test leads, form a resonating circuit. The test gate tunes to this resonating frequency when the circuit breaker is closed and locks to it. So this is the frequency response of the circuit breaker in the closed position. So we have the y-axis representing the current and the x-axis representing the frequency. You can see the minimum current is at this frequency, so we look to it. We look to this frequency and we use it for testing. And when you look at the response for when the breaker is open, you can see at this point the current is much higher. So using this way, we can differentiate between when the breaker is closed and when the breaker is open. This is an example result comparing between dynamic capacitance measurement, dual ground method, and the conventional method. You can see there is very little difference between the two. By the way, here, the thicker line represents the closing condition or closed condition, and the thinner line is the open condition. This is another example for a closing operation. Now we'll talk about dual ground timing in GIS or gas insulated switchgear. It has its own set of challenges. This is a simplified diagram of a circuit breaker inside a GIS. We have the main and arcing contacts here. So it's the interrupter. And this is the body of the GIS, the external body. And we have two earth switches on the left and on the right. This earth switch connects this part of the circuit breaker directly to earth. And this earth switch connects this part, the left part of the circuit breaker, to this part of the GIS body. Then through this earth link, it is connected back to the ground or earth. When we remove this earth link or shunt, this part of the body is insulated from this part through this insulation. So right now, this part of the circuit breaker is not grounded because we removed the earth link. And this is what we do usually when we want to do circuit breaker timing using the conventional method. So we remove the link and we connect two leads where this link was and connect our circuit breaker analyzer. So this lead will be connected through the body to this part of the circuit breaker, the right side, and this lead will be connected to the left side of the circuit breaker. So now we can do timing test the usual method. But again, this raises a safety issue, might damage your equipment. And when you are removing this earth link or shunt, you might get arcing and you might get severe burns. What we did at Megger is we took a material called ferrite. You might see it on charging cables, similar material to that. This ferrite acts as a filter for, let's say, higher frequencies. So the shunt will still be there and will be connecting these two parts together at rated frequency, but at the higher frequencies that we are using for testing, these frequencies will be blocked. So now we can connect our circuit breaker analyzer through this accessory DCM, dynamic capacitance measurement, across this ferrite. And as for the circuit breaker analyzer is concerned, it will see an open circuit here, but the earth link is still there. This is how the ferrites look like. We have C-type and I-type. You will close these on the both sides of the earth link, and we have a strap to hold them in place. If you have a bigger earth link, you can use C and C type for bigger earth links. And for earthing cables, we have the clamp type or round type ferrite. This is a real example of a Siemens 8DN9 or 8DN8 breaker. We have an earth bar that's connecting phase A and phase B and phase E to earth. So we'll need multiple ferrites here to isolate at high frequencies only for between phase C and earth and phase B, again phase B and earth, and between earth and phase A. You can see the ferrites connected here. And here are the clamps that we will connect the test leads to. This is another example for 8DN9 breaker. You can see the ferrites connected here. We have the test leads connected here. Our last example is for an ABB ELK02. You can see the test leads here. And we have the ferrites connected here. Another important test is coil current analysis. In this test, the current is drawn by the coil during the operation of the breaker and is measured. It might be intimidating at first when you first look at the graph, but it's quite easy to understand. This graph gives us valuable information about the condition of your coil. So let's see what happens in this graph. Here, at the beginning, the contact is closed and the coil starts energizing. At this stage, the armature or the plunger start moving, and then it hits the latch of the tripping mechanism for the circuit breaker. That's why you see a dip here in the current. And then here the armature finally finishes the motion and hits the stop. So now the current increases gradually till it reaches the steady state. This current can be calculated by dividing the DC voltage by the resistance of the coil. So at point number 8 here, we have the opening of the auxiliary contact to protect the coil. So the current decays and reaches back to 0. An important information we can find from this graph is, of course, the coil resistance. We can verify it from here. We can measure the voltage as well as the current from the graph here. Use Ohm's law and get the resistance of this coil. Another thing is we can get back to this graph when we have any issue with our timing measurement, because the delay might be caused by a delay in the armature or the plunger. So you might see this part of the graph, instead of taking, let's say, 30 milliseconds, it will take, for example, 20 milliseconds. This might be caused of or due to bad lubrication, especially if the breaker have not been operated since a long time. The next test that we'll talk about that is often neglected or overlooked is motion measurement. It is a very important test as it gives us information about our breaker that the timing test does not. This test is done by measuring the contact travel during operation using transducers that convert the movement into a measurable signal. It gives you a graph that we can get information from, like closing and opening speed. If the movement is too slow, this might cause problems with extinguishing the arc. If it's too fast, it might cause mechanical damage. Contact stroke measurement makes sure that there is enough gap and isolation when the interrupter opens, and that there is a good contact when the breaker is closed. The motion graph also gives us information about the damping. When the damping is too low, you might get over travel and the mechanism might get damaged. If you have excess damping, the moving contact will be slower in the arcing zone, so the arc won't be extinguished as fast. Finally, if the contact rebounds, it might cause reignition of the arc and the breaker might explode. This is an example of a travel or motion graph. Let me open it to explain this graph. So we have two states here. We have the open position here and the closed position here. This graph shows a close open sequence. So when the coil is first energized and it closes the breaker, the contacts start moving and separating. Keeps moving till we reach this point. You can see the timing result overlaid on top of the motion results. You can see at this point, this is the first touch of the contacts. However, we still have penetration of the contacts until it reaches the full stroke. So the stroke is measured like this, the full distance between the open position and the closed position. So this is my stroke. And we have also contact penetration. It's the distance between the first touch and the full stroke. Then we have an open command issued again. So the contacts start separating at this point. It starts moving here, and at this point, it starts separating. And continues opening. This zone or this area is called the arcing zone. And you don't want your contacts to be here for a long time because the arcing will damage your contacts, especially the arcing contacts. And then we have the damping zone where the kinetic energy of your breaker is absorbed. We can do or measure the velocity of the breaker at 2 points or at 2 stages. So for the closing stage, we will take the linear part, which is this part. We'll take 2 points. So we have the distance between the 2 points and the time difference, so we can calculate the velocity. Same thing for the opening. We'll select 2 points at the linear stage of the curve. Regarding the damping, if the damping is too low, the movement speed of the breaker in this region will be very fast, and this might cause damage to the mechanism. If it's too slow, like this, for example, it might take too long for it to exit the arcing zone, and this might damage or burn your arcing contacts. The motion measurement is translated, as I said before, using the transducers. We have two types of those. We have linear transducers, which translates linear measurement, and we have rotary transducers, which translates the circular measurement. This is an example of one of our linear transducer mounting kits. We have generic ones and we have manufacturing or manufacturer specific ones. And this is an example for the rotary transducer mounting kit. This picture shows how the linear transducers is installed for a bulk oil breaker. We have direct linear measurement here. You can see this is the transducer, and you have the cable going to the test kit. These are another example, but for a rotary transducer. So to understand the importance of motion measurement, we have some study cases. You can see in this curve, in this region, we have high rebound of the contacts. The specified rebound, according to the specific breaker, should not exceed 5 millimeter. However, when they measured it, it exceeded 11.5 millimeters. The dashpot was adjusted, and they did the motion test again, and you can see here there is no that big of a rebound. But when they measured the stroke, it's not according to the specification. I have 104 versus 109 millimeter. So the dashpot was over adjusted, let's say. They adjusted it again, tuned it again, and they did the test. And these are the two results overlaid on top of each other. We can see the stroke was fixed, and now it reached the specified 109 millimeter. So when you compare the two results, you can see there is not much of a change between the timing of the circuit breaker. So if we did not do a motion measurement, we might have missed this issue in the circuit breaker, and over time this might cause a damage to the mechanism of the circuit breaker. This is another case. We have the timing results here. We can see all of the results have pass grades, let's say. However, when we did a timing test, you can see we have three graphs. This is a separate mechanism breaker. That's why we have one for phase A, one for phase B, and one for phase C. We can see the timing results are good. However, we can see extreme speed in this region for phase C when we look at the motion results. You can see the phase A is 6.83 meters per second, whereas phase B is 9.335 meters per second. So the mechanism was fixed, and we can see the three motion curves are basically on top of each other. The last test that we are going to talk about today is the dynamic resistance measurement. It is a test used to assess the condition of the arcing contacts in SF6 circuit breakers. So when we are doing static resistance measurement, we can't really assess the condition of the arcing contacts because the main contacts has very high, very lower resistance when compared to the arcing contacts, and they are both parallel when the breaker is in closed state. So for this example, we have a 30 micro ohm main contact and 1000 micro ohm arcing contact. When you measure the equivalent resistance, 30 parallel with 1000, you get 29.12 microohms. So it's very difficult to find or detect faults in the arcing contact using the static measurement. However, when we do a dynamic resistance measurement, we are basically measuring the resistance of the circuit breaker continuously while opening the circuit breaker. At certain point, we will have the arcing contacts only connected. The moving contact will be disconnected. So we can measure the arcing contact resistance at that point. This is an example graph of dynamic resistance measurement. As you can see, it's very difficult to get a resistance value from this graph. You can see it's very spiky or very noisy, let's say. So this region represents the closed position. And when we issue a command for the breaker to open, and the breaker starts opening, we will get a spike here. This spike represents the separation of the main contacts, and the second spike represents the separation of the arcing contacts. However, with this graph alone, we can't do anything with this value. It doesn't give us any information about the condition of the arcing contacts. But what we can do is do a motion measurement along at the same time with a dynamic resistance measurement. With this information, we can link them together. So we can take the distance at this point and this point. So the point where the main contacts separate and the point where the arcing contact separates, and get the difference in distance between them. And this represents the length of the arcing contact for me. We have a case study to show that. So this is a new generator circuit breaker that we have tested before. And you can see the arcing contact length is about 15.47 millimeters. There was a short circuit fault on this GCB, and we did a test again on the same breaker after the fault, and we can see that the length reduced to 7.07 millimeters. This picture shows the contact assembly after they opened the breaker to inspect it. This is a newer one, and this is the one where the short circuit fault occurred. You can see it's very deteriorated. It's for the moving contacts. And this is the fixed contact. You can see it burned. There's much carbonization. And you can see the length. There's a difference in length that we can detect using the dynamic resistance measurement. So to conclude, now we know that the dynamic resistance measurement adds little time to overall testing. You can perform it while doing the motion measurement or travel measurement. And it's non-invasive. You don't have to open the breaker and remove the SF6 gas, which is very time consuming and very expensive, just to inspect your arcing contacts. You can do the dynamic resistance measurement, and when you detect any anomalies, you can open your circuit breaker to change the arcing contacts. It's good to use high current for this test for getting maximum resolution. And you can use previous results to do trending and notice the difference in the length of the arcing contacts. So now we'll talk about some of our solutions that we offer for circuit breaker testing. First, we have the contact resistance testers, the LRO and the Mueller. The Mueller can perform static resistance measurement with dual ground, so no need for removing the earth links. And next, we have the circuit breaker analyzers. We have the older EGIR, which most of you are probably familiar with, and the higher end TM1700 and TM1800 range. And we have also the VIDAR, which is a vacuum integrity checker for vacuum circuit breakers. But the product that I want to focus on today is the EGIL 200. It's a device that we recently launched, and I think it's the most suitable for our region, given the circuit breaker types that we have here. So it's a mid-range circuit breaker. It fits between the, let's say, older EGIL and the higher end TM1800 and TM1700. It is very intuitive to use, and its measurement channels is inherited from the TM1800 and 1700 series, so you can rely on its accuracy. We have many different models for the EGIL 200, but the two models that I advise usually for this region is the EGIL 211 and EGIL 213. They both can do timing test for one break per phase. When you want to test more than one break per phase, you can use the dynamic or the dynamic capacitance measurement method, dual ground method. It can support up to 4 breaks per phase. The main difference between these two units is that 211 has 1 analog channel and the 213 has 3 analog channels. So if you want to do dynamic resistance measurement for 3 phases, we advise going for EGIL 213. This is how the main screen looks in the EGIL 200 built-in touch screen. You can see it's very intuitive to use. It looks like an Android app. The first row represents the test object. You can divide. You can set how many number of phases you want to test. Is it a common or separate mechanism breaker, and the number of breaks. And you can select if you have a pre-insertion resistance or not. Usually not in this region. I rarely see using pre-insertion resistance in our circuit breakers. And you can select in the second row the type of the test. What do you want to measure? Timing test, motion test, and do you want to use single ground, conventional method, or dual ground using dynamic capacitance measurement? Finally, you select how do you want to measure it. These are the tests supported by the EGIL 200 series. Can do timing for main and pre-insertion resistor contacts, coil current analysis for the closing coil as well as open 1 and open 2 coils. You can perform station voltage measurement to find issues with your DC battery voltage system. Motion measurement, static contact resistance as well as dynamic resistance measurement. You can also measure the current drawn by the charging motor as well as minimum pickup voltage for the closing as well as opening and open 2 coils. We have also alternate testing methods like first trip test. In this test, let's say you have a breaker that has not operated for a long time. You know that if you open it or perform an operation for the first time, it might take a bit higher time for opening because you know the lubrication might have dried out. So you don't want to lose this information. So we have a first trip kit. This consists of clamps that will be connected to the coils. Let's say the opening coil, and other clamps that are connected to the secondary of the CTs. So when you connect to the secondary of the CTs, you will measure the load current that is passing through the breaker. And when the breaker opens, this current will stop. So you can, from this, you can detect the status of the breaker. So now we can perform a timing test without, let's say, de-energizing the circuit breaker. So we don't lose this valuable information. We can also do a timing test via the voltage detecting system and medium voltage GIS. All tests performed by the EGL 200 are saved in the local storage, and you have the option to either export it as a test file or PDF through USB, or print the result using the built-in thermal printer. Regarding the accessories, we have the DCM 200 accessory. It is used for performing dual ground. We also have the ferrite kit that we have discussed earlier. Finally, we have the SDRM, static and dynamic resistance measurement kit for measuring static and dynamic resistance, as the name suggests. So that's it for today. Now we are open to receive your questions.
Thank you, Engineer Ali, for the informative sessions. I can see that we have few questions in the chat box. First of all, let me just remind you all that all the recordings will be shared within the next 2 days, and you may use the form that is pasted in the chat box to request product demo or attendance certificate or anything if you have further questions to the for the speaker. Also, I would recommend you to follow us on social media accounts, Facebook and LinkedIn, to find all new updates about products and webinars. Just a second. So, Mr. Ali, the first question is, the circuit breaker timing test is the test. So my last supervisor tells me that circuit breaker timing test is a test to measure the time of opening, closing, and contact bounds, not opening, closing only.
I don't think it's a question, it's more of a statement, and you are correct. The timing test not only gives us the closing time and opening time, you can get the bouncing or the bouncing time of when during the opening and closing operations. Yes, you're correct.
So the next question is, what is the accepted deviation value between phases of medium voltage circuit breakers in CRT and the accepted result of CRT?
I'm not sure what he means by CRT. If he can just elaborate on that.
I think the contact resistance testing, maybe.
Let's see. What is this device? Let's see. Maybe if he can elaborate, so we can answer his question.
Okay, so next question is, if the circuit breaker has not tripped for a long time, what tests are required to be conducted online? What is OEM recommendation?
So if a circuit breaker has not been operated in a long time, we recommend performing we call it a first trip test that I just discussed. Because when you do a timing test using the conventional method, what you will do is open the breaker to isolate it so you can test. So the first time it might take a bit longer to operate, but you are not connecting any equipment for that, the first operation. So you miss that data. So using the first trip kit, you connect the clamps on the secondary of the CTs to measure whether there is a load current flowing or not. So when the breaker opens, the current flow will be stopped. So you know that your breaker is opened. So from that, we can measure the timing test without first isolating the breaker.
Okay.
So I hope that answers your question.
The next question is, what are the accepted values of insulation resistant test for MVCP?
So the insulation, the accepted insulation resistance value will depend on the specific breaker and the specific voltage level of that breaker.
Okay.
Did we get any elaboration about that question about the CRT?
So let me remind you all that you can use the raise hand feature to ask your question verbally. Maybe it's going to be clear for the speaker and for yourselves. So what is the duration to test the MVCP timing test and relay testing?
Sorry, so can you repeat the question?
What is the duration to test the MVCP timing test and relay testing? So what is the duration to test?
Two questions. So for the breakers and the relays. So this will depend on the utility or the company you are working with. Each one has a specific schedule for that. However, you can refer back to the standard for the recommended, let's say, duration.
Mr. Ali, I see one raised hand, so I'm just gonna. Mr. Santel?
Yes, you can unmute him so he can ask his question.
Yeah. Go ahead.
Ganapati. This is regarding the breaker, just to explain the first trip test. Suppose if the breaker has not operated, has not tripped for a longer time, the breaker is in service, the line is energized.
Yes.
But if I want to do the first trip test, I'm not supposed to open the breaker. Breaker should be kept online. I cannot trip the breaker because the line will be with a load.
For this test, it has to have some load because otherwise we can't detect if it's open or closed because we are using the current on the secondary of the CTs. So
which means we have to open the breaker, right? Breaker has to be tripped.
Yes.
So, but we cannot trip the system because we have to keep the breaker on.
Okay, but either way, before doing the normal way for timing test, you will have to to open the breaker to isolate it for testing. So either way, you will have to open the breaker.
But many breaker in our system for longer time, maybe it might not have tripped. Maybe we will be expecting that breaker should trip as per the requirement.
Yeah, the expectation is that it should trip within the specified time by the manual, but you are doing the test to verify that, because if it has not been operated for a long time, the loop so it might get some delays, let's say, for the first few operations. If you open it and close it, let's say multiple times, it might get back to the normal operating time.
Okay. Thank you.
You're welcome.
So I see in the comment section that there are more specific industry-related questions. I recommend you to go to the webinar questionnaire and just select the option which says you have a technical question for the speaker to contact you directly on your email or by phone, just to discuss this case with you, because it's more specific to your field, test field. Or you can email us on memarketing@megger.com and we can answer your questions directly. So I think we can end the session today at this point. Please be reminded that we're gonna send the recording within the next 2 days, and you may request an attendance certificate or quote or demo by answering the quick survey question. So thank you all for joining, and thank you, Mr. Ali Azzam, for the informative session, and we hope to see you all soon.
Thank you all. See you. Goodbye.